Today we learn about geodesics. Geodesics are essentially equivalent of straight lines inside Riemannian manifolds. They're among the most important objects in Riemannian geometry, and in fact, there are mathematicians out there spending their lives studying geodesics. Okay, to see what is a geodesic, let's go back to Euclidean geometry. I guess some of us learned Euclidean geometry in high school. Let's do a quick review. What is the main kind of object, main hero of Euclidean geometry? I would say straight line. Straight lines are essential in Euclidean geometry. We use kind of bits and segments of straight lines to construct most of the objects in Euclidean geometry, right? Like triangles, squares, rectangles, etc. Okay, what are the essential properties of straight lines? Well, one important property is that they give us the shortest path between any 2 points. Let's say we have 2 points P and Q. There are different ways to connect P to Q. We can use different curves to go from P to Q. Which one is the shortest? The segment which is part of a straight line. That has the shortest length among any other curve or any path going from P to Q. The essential important property of lines and segments is their existence. For any 2 points P and Q on the plane, there is a straight line going from P to Q. There's a line connecting them. In fact, if we assume they're not the same point, P and Q are two different points, there's just one line connecting them, right? Okay, here we have 2 points P and Q and one line going through P and Q. And as I mentioned, the other essential property is the uniqueness. If P and Q are two different points, there's exactly one line, just one line connecting them, not more, not two, right? Exactly one. Okay, what else? What are the other important properties of lines, straight lines in Euclidean geometry? What else comes to your mind? Well, one thing is that the equation which describe lines, which you might not take that as part of Euclidean geometry, but anyways, it's a linear equation, I mean, because it's a line. So if you think about the plane given by coordinates x and y, the equation of a line is given by ax plus by plus c equal to 0, where a, b, c are constants, right? We can use the parametric equation to describe line. What does that mean? So again, fix x and y as coordinates. We can think about x as a function of an extra parameter t. We can say x is given by at plus x naught, y is given by bt plus y naught. Here a and b are two constants, x naught and y naught are also constants. T is our parameter. T goes from minus infinity to infinity. This way, we think about x and y as functions of t. Okay, just a simple thing. If we take derivative of x with respect to t, we get a, the constant. If we take derivative of y with respect to the parameter of the line t, we get another constant b. If we take the second derivative of x with respect to the parameter t, we get 0. Derivative of the constant a is 0. The second derivative of y with respect to t is also 0. Actually, these two simple equations, second derivative of x with respect to parameter t, you can think about it as time is 0, the second derivative of y with respect to t is 0, they're essential in understanding straight lines. Okay, great. Now, there is a different kind of essential property of straight lines. Look at this curved line, and let's compare it with a straight line. Suppose we have a particle which is walking along this line, let's say with constant speed. So it's like parameterizing these two curves. Let's say gamma 1 is a curve from, say, some interval ab to r squared, and gamma 2 is another curve from another interval maybe, we're saying, to r2. That should be r2, I'm sorry. So the point is that if we look at the velocity vector, if we take derivative of gamma 1 with respect to t, we get the velocity vector. It's the vector tangent to the curve, okay? Let's look at this curve along, let's look at this tangent vector along the curve. Okay, The essential thing is that the direction of this kind of tangent vector along the curve is changing. Even if we fix its length to be constant, if we walk with constants, but the direction of the curve is changing. What about gamma 2? The point is that gamma dot, the derivative of the curve of this parametrization, is staying constant along the straight line. This is quite essential. So gamma 2 dot is constant, whereas gamma 1 dot is not, right? So let's try to kind of characterize straight lines with this property. Straight line is a line where the derivative of the curve along the curve is constant. Okay? That's actually the way to generalize this notion to curved manifolds. So if we want to go from Euclidean geometry, which everything is flat, everything is kind of rigid, to the world of Riemannian geometry, where everything is curved, right? It's not like R2, it's not a vector space. Everything is curved, but there is a metric. If we want to kind of extend this notion from R2 to manifolds, if we want to extend the notion of straight lines from R2 to Riemannian manifolds, let's say M and G, the pair M and G is a Riemannian manifold, this is the correct way to kind of define what the equivalent of straight line should be. Think about two spheres like the surface of the Earth. Suppose you're at that red dot. Suppose you want to walk on a straight line. So that red kind of curve feels like a straight line when you're walking on the surface of the Earth. Although Earth itself is curved, it feels to you when you are on that point, when you're walking on the surface of the Earth, it kind of feels to you as you're walking on a straight line. That is what is known as geodesic. Geodesics are essentially the generalization of straight lines in Riemannian geometry. How should we define them? Okay, so let's say gamma is a kind of a curve from some interval AB to our Riemannian manifold M. I would say this curve is a geodesic. For instance, that great circle on the sphere is an example of such. If it has the same essential quantity as straight lines, if the derivative of curve, gamma dot, is constant along the curve, okay? So, loosely speaking, gamma dot is like velocity. The change of the gamma dot is like acceleration. So it's kind of like saying gamma dot is constant, it's like its change or its derivative is zero, which means it's kind of like the acceleration of a particle moving along a geodesic with constant speed is zero. Okay, so remember, when we have a Riemannian metric on a manifold, there is a unique compatible symmetric connection on that manifold called the Levi-Civita connection. If you didn't see this, you can go to look at the previous lecture. So saying gamma dot is constant along the curve, it means the change of gamma dot along the curve is zero, where the change is given by the Levi-Civita connection. But change in the direction of the curve, along the curve. What is the direction of the curve? Gamma dot itself. So it essentially means the covariant derivative of gamma dot in the direction of gamma dot is zero. I would say gamma is a geodesic if it satisfies this equation. This is called the geodesic equation. So look at this equation a bit. This is the essential equation. Gamma is a geodesic if derivative of gamma dot in the direction of gamma dot vanishes. Okay. Just a quick lemma. This is not very hard to see. That when we have a geodesic, let's say gamma is a geodesic, the solution to that equation, derivative of gamma dot in direction gamma dot being zero, the natural parameterization it's given by is an arc length parameterization, in the sense that if you look at the derivative gamma dot, its norm, which is the norm of velocity vector, which is kind of like speed, is constant, which makes sense. The definition of geodesic is Gamma dot should be constant. So it kind of makes sense for its norm also to be constant, right? But let's give kind of a more mathematically rigorous proof of that. What does it mean for the norm of gamma dot to be constant, for norm of this vector to be constant? It means it doesn't change when the parameter t, time parameter, or whatever it changes. So its derivative with respect to t is 0, right? That's essentially what it means. But for the sake of proof, note that saying the norm of gamma dot is constant would be the same as saying the norm of gamma dot squared is constant, right? Kind of proving the derivative of gamma dot squared with respect to time is 0 is slightly more straightforward, easier to work with. So what is the norm of gamma dot squared? It's inner product of gamma dot with itself. So let's show the inner product with g. It's g of gamma dot and gamma dot. So we want to say derivative of this thing with respect to time is 0. But remember, its inner product is like a product. So we had this product rule. It's like taking derivative would be like taking derivative of first component times the second component plus first component times derivative of the second component. That's true when our connection is compatible with the metric. But now the first component is derivative of gamma dot in the direction of gamma dot. By the definition of geodesic, that's 0. Same happens for the second component. So derivative of the norm of gamma dot squared with respect to t is 0. So it's constant. It doesn't change. Okay, that's just a good kind of simple exercise. Okay, for the next step, let's get back to the equation of straight lines in planes. So let's say this is R2. This is a straight line here. It's given by some kind of parametric equation for xt and yt. So x and y are things along this line. We learned that the second derivative of x with respect to t is 0, second derivative of y with respect to t is 0. And I mentioned these two equations are kind of essential. So what would be the analogous of these equations for geodesics on a Riemannian manifold? This is kind of important. So let's say gamma is our curve, right? Let's say it's a geodesic. So it's given by the geodesic equation. We know it satisfies the geodesic equation. It's a geodesic in a Riemannian manifold MG. So let's say this is also schematically our manifold. Here it looks like a surface. Now let's choose kind of a region, small region in the manifold where we have coordinates there. Okay, a local kind of, we have, let's say, local coordinates there. So let's say x1, x2, up to xm are local coordinates on our manifold. Okay, great. And let's say a piece of our geodesic gamma, which is given by, in coordinates, is given by gamma 1 of t, gamma 2 of t, up to gamma m of t, falls inside this region. So I'm going to denote that with this red kind of piece. Let's say this is my geodesic. Okay? So what is the equation for this gamma 1 up to gamma m in these coordinates? What is the equation for each gamma I? So if we want to just naively guess, one might say, if I want to copy the equation for straight lines and say maybe they are correct for any geodesic, one naive guess might be that the second derivative of gamma I with respect to t, so d squared of gamma I over dt squared should be 0. That would be a naive guess. It's just kind of naively generalizing the equations for straight lines to geodesics. Is that correct? So the answer is no, not exactly. This is not the exactly correct equation. So remember, the equation for geodesics is the following. Gamma is a geodesic if its derivative of gamma dot in the direction of gamma dot is 0, right? That's our equation. Let's write down, we should write down this equation in coordinates to see what we would get. In lecture number 9, I guess, we were discussing Levi-Civita connection, or Christoffel symbols, I guess, in fact. We discussed what is the formula for covariant derivative of x in direction of y. We should take that formula, Replace both x and y with gamma dot. So if we have a formula for derivative of x in direction of y, if we replace that with gamma dot and gamma dot, we get what we want. So just a quick review. If we pick partial x1 up to partial xm to be our basis vectors, we learn derivative of xi in direction xj is given by this Christoffel symbol equation. It would be a linear combination of partial xk where each coefficient is gamma k ij, right? Christoffel symbols. So if you do that, I'm not going to do the details. If you just exactly write what is covariant derivative of x in direction y, replace x and y with gamma dot, that being equal to 0 gives you the following. For every k from 1 to m, we get one formula. So for every k, where k can be 1 to up to m, we have this thing, that the second derivative of gamma k with respect to the parameter t plus sigma Christoffel symbols time derivative of gamma I dt d gamma j dt equals 0. So just to understand this equation, when we are working with R2, k can be only 1 and 2. Here in this equation, k goes from 1 to the dimension m. So this is actually their m equations here. For each k from 1 to m, we get a different equation. On R2, all of these Christoffel symbols are 0. So the whole sigma disappears. What do we get? The second derivative of gamma 1 with respect to t is 0, second derivative of gamma 2 with respect to t equals 0. All the Christoffel symbol terms would disappear. If we just do change of variable, if we call gamma 1 x, gamma 2 y, we get exactly the equation we saw. Second derivative of x with respect to t vanishes, second derivative of y with respect to t vanishes. So this thing is like the honest generalization of that line equation we had to Riemannian manifolds. Okay, great. Now, two important questions. One is the question of existence. So, kind of an essential thing in Euclidean geometry we have is that for any two lines, there is a line which passes through them, right? For any 2 point P and Q, there's a line passing through them. We can look at that segment, part of the line, that would be the shortest path. Do we have that for manifolds? If I have a Riemannian manifold, if I pick a point P, another point Q, is there necessarily a geodesic connecting them? So in this kind of illustration, we do. There is like a line connecting them. That's a geodesic. In fact, in the case where we are working with arbitrary manifolds, that might not be true. So a counter example would be R2 minus the origin. Let's say that's our whole manifold. Pick R2, remove the origin. Now, if I look at the points minus 1 and 0 and plus 1 and 0 to be my 2 points P and Q, there is no geodesic connecting them inside this manifold. So the only geodesic potentially connecting them would be this blue segment. But that's not a good geodesic because that is not inside my manifold. My manifold is R2 minus the origin. So the problem with this manifold is that this has a hole. So in more technical word, it's not complete. And that's essentially the problem. In fact, if our manifold is complete, then it is correct. For any 2 points, there is a shortest geodesic connecting them. So a kind of special case of this theorem would be if you have a compact manifold would be complete. Then for any 2 points you pick, there is a shortest geodesic connecting these 2 points. The other question is the question of uniqueness. Again, in Euclidean geometry, there is exactly one line connecting two distinct points, not more, right? Is it true for Riemannian manifolds? If I pick 2 points, is there exactly one geodesic connecting them? So this is also not true in general, especially if your points are far away or if you look at longer geodesics. So let's consider, to understand this, let's consider two spheres. And let's say we have 2 points P and Q. Let's say they're antipodal points, right? So you see there are different geodesics connecting them. We did not prove this, But when we have this standard round sphere, geodesics are essentially the same as the great circles around the sphere. So you can see we have a great sphere going from P to Q, let's say this red one, but there is another one, right? The blue one. But there are more, much more. We can take this pink one. So you see there are many geodesics going through P and Q. We don't have the uniqueness anymore. Okay, great. So with this understanding, let's get back to the problem of existence, the kind of essential, important problem for geodesics. So this is true. So as I said, if your manifold is complete, this is a correct statement. Let's say schematically, this is our manifold. The surface with genus 4, let's say. Let's say P and Q are 2 points. They can be very far from each other. So the statement or the question is that, is there always a geodesic being shortest curve connecting P to Q? And the answer is yes. There is always something like that if we have the completeness assumption. So the statement would be if M and G is a complete or more specially a compact manifold, then for any 2 points P and Q in M, there is a shortest curve, a shortest geodesic connecting P to Q. So that is our existence statement. In fact, we can make this a bit more nuanced. There is a bit more we have actually a better description of this theorem. So in order to state it in a slightly better way, we need something from algebraic topology. And that is related to homotopy or homotopy classes. So let me just give a very, very shallow intuitive description of that. Consider the torus, the surface of a donut. Let's say P and Q are 2 points. They're different, but just let's say we pick a curve, the pink one, a pink curve from P to Q. Now we can slightly deform this pink curve to get to that red curve. Just push it around a little bit. We can push it more to get to this orange curve. But there is no way by just pushing it around we can get to that blue curve. There is no way to push this curve on the torus to go through that hole. Also, look at this other orange curve. It goes around the hole once and then goes to Q. Again, we cannot play with these curves to deform them to this orange one. We would say these different curves are different homotopy classes. The other way of saying it is that two curves, gamma 1 and gamma 2, are homotopic or are in the same homotopy class. If you can deform one to the other while you're fixing the initial and terminal final points. Okay. Now, one can make this statement about geodesics even slightly more accurate. The point is that if I have 2 points P and Q, in each homotopy class, there is a shortest geodesic in that class. So, for instance, if I look at the curves which go from P to Q, say from the left side of this picture, let's try to kind of sketch one. Let's say this pink one is in one homotopy class. In that homotopy class, there is a shortest geodesic. Let's say this is this one. Let's say this is the shortest one. If I go from the other side of my manifold, let's denote that with this blue one, there is a shortest geodesic in that homotopy class too. Again, note that here we should have the completeness or compactness assumption. Completeness is enough. Assuming the manifold is complete, in each homotopy class, we have a shortest geodesic. It's not, again, unique. We just saw that in the other example on two sphere. There might be more than one, but there is at least one. Okay, the proof is kind of uses heat flow. A good reference for that is this book by Jürgen Jost, Riemannian Geometry and Geometric Analysis, section 1.6. 7th edition is a good one. The section is called Heat Flow and the Existence of Geodesics. I'm going just to give a very, very shallow rough idea of that. If you like to see real detailed proof, not actually complete, but with more details, you can take a look at that book. So I want to show for any P and Q in any homotopy class, there is a shortest geodesic connecting them, which is essentially equivalent to this statement in Euclidean geometry that for any 2 points we have straight line connecting them. So the idea is that pick any curve in the given homotopy class you want. Let's denote that with gamma naught from P to Q. Gamma 0 or gamma naught, it's a curve connecting them. The manifold is assumed to be connected. Let's connect P to Q. It doesn't have to be geodesic. Just pick any curve you want. Say any smooth curve. The idea is that I want to start to deform this curve so that it becomes shorter and shorter. So I construct one parameter family of curves, gamma tau, for tau being positive, where when tau is 0, it's the one I started with, but as tau is becoming larger and larger, I just deform this curve, evolve this curve to become geodesic. So I get a flow of curves. I get like a sequence or one parameter family of curves. You see, in this case, you see you are seeing like more and more kind of shorter and shorter curves. We see more curves. At each state, you try to deform your curve a bit, so it becomes a bit shorter. And as time goes to infinity, you want to get converge to that geodesic, to that shortest curve. This is a very common idea in math. You start with an object, you start to modify it in a direction of becoming better or closer to the object you want. In order to do so, you need to have an evolution equation. So you want to say, I start from gamma naught, I modify it, I deform it a bit so it becomes shorter. I keep on doing that until I get to the geodesic, to the shortest one, maybe after infinite amount of time. For doing so, you must have a rule, how you would modify. What is the equation for the curve to evolve? This is what is known as heat flow for harmonic maps or geodesics. So I just write the equation. So I should say how you should change your curve. I'm denoting tau as this new parameter which says how your curve should be changing. So t is the parameter along each curve and tau is the direction the curve should be changing. So the heat equation or heat flow says for each k from 1 to m, for each component of your curve, the change of curve with respect to the parameter tau is given by this. On the right hand side, I exactly have what we had as the geodesic equation. So the second derivative of gamma k with respect to t plus sigma multiplication of Christoffel symbols times derivative of gamma I with respect to t, derivative of gamma j with respect to t. So the right-hand side is the equation that we said if it's equal to 0, your curve is a geodesic. I just put that on the right-hand side. So this tells you what is the kind of gives you the direction you should be modifying your curve. And as you're doing, your curve in fact becomes shorter and shorter. What happens if you start with a geodesic? So if your gamma dot, the curve you start with is a geodesic, the right-hand side is 0. The right-hand side is exactly the equation we saw for geodesic. If the right-hand side is 0, the left-hand side would be 0. The left-hand side is telling you how you should modify your curve. If it's 0, it means don't do anything. Don't touch your curve. You see, that's a good sign. If you start with a geodesic, it doesn't change that. If it's not a geodesic, it would push it in a direction to make it shorter. And at the end, it would converge to a geodesic.